Pre-Calculus 3.4, Day 1, solving simple exponential and logarithmic equations. And we have this box for some strategies for solving. And so rewrite the original equation in a form that allows use of 1-to-1, or rewrite an exponential in logarithmic form and apply the inverse property of logarithms, or rewrite a logarithmic in exponential and apply inverse property of exponential. So you're just going to have to look at the structures on these and kind of notice how they're similar, how they're different, and kind of memorize the different processes that you use to solve these. And one thing that says you should use logs to solve is when you have variables as exponents. So when you're looking at part A, you have these variables of x as exponents. And the base of e is just a number, right? E is about 2.7. And so that's an indication that it's a good time to use logs to solve. And so since we have a base of e, I would choose to take the natural log of both sides. So if I have natural log of e to the negative x squared equals natural log of e to the 5x plus 6, then since we have the exponents of negative x squared and 5x plus 6, we're going to bring those out in front. And when you bring out the binomial of 5x plus 6, it must be in parentheses to get full credit, because that entire binomial is being multiplied by natural log of e. But at this point, you want to have memorized that the natural log of e is 1. E to what power is e? E to the first. And so then we have a negative x squared times 1, and we have this quantity 5x plus 6 times 1, which is just a minus x squared equals 5x plus 6, and set that equal to 0. And that factors. And so my solutions are x is equal to negative 2 and negative 3. And e to the x, the domain of those functions are all real, so there's no restrictions on those, so those are your answers. Now, there is an alternative way to see this problem. It's kind of unique. It does not always happen. But since these are both base e, in order for these two to be equal, their arguments would have to be equal. And if you see that, that's using that use of 1-to-1, and that can't always be done. But in this case, they're both the same base, so the only way those two sides are going to be equal is if negative x squared equals 5x plus 6, and then the solving of that is going to be the same as what we did as we worked it before. So it's just an alternate way to see that one. A little less work, but it's not always something you can do. So on this next one, unfortunately, this should have been for 3 to the x equaling 64. So anyway, so 3 to the x equaling 64, that's how it should be written. Sometimes when we transfer those, they don't transfer the way we want them to. Sorry about that. And so anyways, when you see this base of 3 raised to a variable, you want to isolate it. That's very important. Isolate the base raised to the variable exponent. You want to do that first before trying to, oftentimes you need to use logs to solve this because you have a variable as an exponent, but you want to isolate the 3, which is the base raised to the x first. So you want to divide by 4. That needs to be the first step that you do. And you divide both sides by 4, you get 3 to the x equals 16. Now, we are not going to be able to use the 1-to-1 property because 16 is not a nice, neat power of 3. But we have a variable as an exponent, so the only way to get that down is to take the log of both sides. This is not set up for 1 to 1. And so the only way to get the variable out of that exponent position is to take the log. Excuse me. And at this stage, we usually go to the natural log and take the natural log of both sides. So we're going to take natural log of 3x to the x and natural log of 16. So we're going to take the log of both of those. And then I can use the properties of logs and bring the x out in front. And if I solve for x is natural log of 16 divided by natural log of 3. This, if I ask for my exact answer, this is the exact answer. Or the approximation, put that into your calculator and divide it out, is about 2.524. That is approximate. Sometimes people think when they put it in the calculator that decimal is the exact, and it's not. The natural log of 16 over natural log of 3 is the exact answer. All right, solve each equation and approximate the result to 3 decimal places if necessary. So here we have a base of e. Remember, e is a numerical value, about 2.7, raised to a variable. So isolate the base of e that's raised to the variable. And so subtract 5 on both sides. And I have a minus 3e to the x equals a negative 3. Divide by negative 3. And we get e to the x is 1. And now since I have a base of e, I certainly want to take the natural log of both sides. Bring the x out in front. Natural log of 1, though, is 0. And you want to know that. And also, natural log of e is 1. So you get x equals 0 as your solution. X equals 0 as your solution. And if you think back to this step, it makes sense. E to what power is 1? 0. You want to know and have memorized always that natural log of e is 1 and natural log of 1 is 0, so that you can replace those. Okay, in part B, we have the base of 5 raised to an expression that contains a variable, so you need to isolate 5 raised to the 3x minus 4. You want to get it by itself. So the first thing I would do is subtract 1 on both sides. Then you need to divide by 7. You cannot take 7 times 5 and make it 35. It will be wrong because powers come before multiplication. So that's why you need to isolate that base first. So divide by 7. And now I can't use the 1-to-1 property. 5 is not a nice power of 2. So to get that variable out of the exponent spot, I'm going to take the log of both sides. And we're going to use the natural log of both sides. Now I can take that exponent of 3x minus 4 out in front, but it's a binomial. So as I said before, in the previous lesson, you need that in parentheses, or in the previous example, you need that in parentheses. And then I would divide both sides by natural log of 5. We're not going to use a decimal here. We want exact values, so it will look like this. Divide both sides by natural log of 5. We're isolating x now, so add 4. And then I want to get this to be one fraction, so for the 4, I want a common denominator. So I'm going to multiply by natural log of 5 over natural log of 5 to get a common denominator there. It's a very fancy one, but then I will have a common denominator so that I have a natural log of 2 plus 4 natural log of 5 all over natural log of 5 equaling 3x. And then to solve for x, I'm going to multiply both sides by 1/3. So I have natural log of 2 plus 4 natural log of 5 all over 3 natural log of 5. And you can't cancel anything on those. And so that would be fine for this is your exact answer. You want to practice putting that in the calculator. You need to get the value of the numerator before you divide by the complete value of the denominator, and that can be a little tricky. So check it out and see if you can come up with 1.477, which would be your approximate to 3 decimal places. Now in part C, you have to recognize that you have an e to the 2x and e to the x, and that the exponent on e to the x is half of the exponent of 2x, and so this is quadratic in nature. I can think of this as, e to the x squared minus 9, that e to the x plus 20. And if I let w be e to the x, w squared would be that e to the 2x. This is, you can think of it as a quadratic, w squared minus 9w plus 20. You have to recognize that e to the 2x as your first term and e to the x as your second is like a quadratic. And then we can factor this. Numbers that multiply to be 20 but add up to -9, a -4 and a -5. And so that means w is 4 or w is 5, but you can't stop with that because the original value or variable is x. So you need to replace w back with what was it equal to, e to the x. And now you need to get down to x equals. And so if you take the natural log of both sides, and bring the x out in front, but natural log of e is 1. So I have x is natural log of 4, or x is natural log of 5. And to 3 decimal places, that's 1.386 or 1.609. You need all algebraic support, meaning you need to get down to the exact values of natural log of 4, natural log of 5. So, and then you can approximate those in your calculators. Now, at the point of where you got, there's a couple of things that you could talk about here. When you got e to the x equals 4, that's an exponential. You could just rewrite it in logarithmic. That means the natural log of 4 is that exponent x. I mean, if you just know that that's how that rewrites from exponential to logarithmic natural logs, that's fine, instead of taking the natural log of both sides. Same thing with e to the x equaling 5 is just natural log of 5 is x. So you could just go right to there in that case. The other thing is you don't have to do a substitution. If you understand when you see this, that you can just factor that using e to the x and an e to the x and things that multiply to be positive 20 add to -9, that's just fine. And then you set e to the x minus 5 equals 0, or e to the x minus 4 equals 0, and then you can keep on going from there. But you need to get down to x equals, and again, x is going to be that natural log of 5, or x is going to be the natural log of 4, as your exact values. So, but you do need to recognize that's quadratic in nature and solve that. So that's it for 3.4 day 1.